Hello and welcome to this concept explainer brought to you by CBSE ScoreLab of ProfSam.com.
Today, we're going to be tackling a really critical topic from Unit 4, moving charges and magnetism.
And that would be torque on a current loop and magnetic dipole.
Yes. And I know this one can seem a little abstract.
To be honest, it always confuses me. I mean, I know the formulas, I've even memorized them for the test, but I never really get what's happening.
What's actually happening inside the wire, you mean?
Exactly. It just feels like abstract math.
Right. Well, do not worry. My promise to you is that by the end of this session, you'll have crystal clear understanding.
Okay.
We'll make this completely exam safe and simple enough that, even students who struggle with physics can grasp the logic without any fear.
That sounds really good. I am definitely ready to learn the logic behind the math.
Excellent. So let's start with a very simple question. You have a ceiling fan in your room, correct?
Yes, of course.
And when you switch it on, it starts spinning. But have you ever stopped to ask yourself, how? How does it actually spin?
Electricity.
Well, yes, but what is the invisible hand inside that motor that's pushing it round and round?
Yeah.
Because, nothing is touching the blades from the outside.
I've actually never thought about it like that. I just thought, electricity goes in, motion comes out. But you're right, something inside must be pushing it.
Exactly. And this is where it gets fascinating. The answer is, well, it's the concept we're studying today.
Really?
Yes. See, at the atomic level, atoms have these unpaired electrons, and they act like tiny magnets. We call them magnetic dipoles.
Okay, tiny magnets.
Now, when you put them in an external magnetic field, they experience a twist.
A twist? You mean like a physical turning force?
A physical turning force, precisely.
Yeah.
This same invisible twist is what drives everything from a tiny compass needle to a giant industrial motor. And that twist, well, that's called torque.
So to understand how everything moves, we have to understand this torque.
Now you're getting it. Okay, so the core idea is about this twisting force. That's what we are hunting for today.
Let's do it.
Right. So let's visualize this with let's call it a zero level idea. Just imagine you have a loop of wire. It could be a rectangle, a circle, whatever.
Okay, a loop.
And there's current flowing through it. Now, if you place this loop inside a magnetic field, it experiences torque.
The twist.
The twist. It starts acting exactly like a magnetic dipole, which is just a fancy name for a magnet with a north and south pole. The external field then tries to align the loop.
Align it with what exactly?
Tries to align the loop with the field itself. Let me give you an analogy. Think of a weather vane. You've seen them, right? The arrows on top of old buildings.
Yes, I've seen them. They spin around when the wind blows.
Precisely. Now, imagine the wind is the external magnetic field.
Yeah.
And the weather vane. That's your current loop.
Okay, wind is the field, vane is the loop.
So when the wind blows, it exerts pressure, a force, on the vane, and it pushes the vane until that arrow aligns perfectly with the direction of the wind.
So once it's pointing in the wind's direction, it just stops spinning.
Yes. That's its equilibrium position. In the same way, the magnetic field exerts forces on our current loop. It creates torque to rotate the loop until its magnetic personality, its dipole moment, aligns with the field.
Okay. Can we make a mental picture of this? I kind of want to see the forces.
Definitely. Let's do that. Close your eyes for a second.
Okay.
Imagine a flat, circular wire loop. It's just lying horizontally on a table in front of you.
Got it. Loop on the table.
Now, imagine invisible red arrows shooting vertically upward. From the floor, straight up to the ceiling, passing through your loop. That's your magnetic field.
Red arrows going up? Okay.
Now, because current is flowing in that loop, magnetic field, it pushes one side of the loop up and it pushes the opposite side of the loop down.
One side up, one side down. So it'll tilt.
It will twist, it will rotate. But here's my question to you. Do you think it will spin forever?
Well, based on the weather vane analogy, I'd say no. It'll probably stop once it aligns with the field.
Absolutely correct. It twists to reach equilibrium. Once it's aligned, the torque becomes zero. If you try to disturb it, the field just pulls it back. And this concept is exactly why we can design electric motors.
Oh, wow.
Without this logic, we'd have no motors, no galvanometers, no way to even understand how a simple compass works.
That makes sense.
Yeah.
But for the exam, we need the derivation and the formula. The diagrams in the book look so complicated.
We'll simplify it. It's time for the technical bridge. Could you open the insert source document I shared?
Yep, got it here.
Can you please read the definition of magnetic moment from there?
Let me find it. Okay, here. Section 4.1, it says, we define the magnetic moment of the current loop as m equals I times A, where the direction of the area vector A is given by the right-hand thumb rule.
Correct. And is there a formula for the torque as well?
Yes, just after. It says torque vector tau equals m cross b.
Perfect. Okay, let's unpack this step by step. This is usually a 3-mark derivation in the board exam, so pay close attention.
Yeah.
We'll take a rectangular loop. Let's say its sides are length A and breadth B.
Okay, a rectangle in a magnetic field. I'm picturing it.
Good. Now let's think about the forces on the arms of this rectangle. First, let's look at the top and bottom arms, the ones with length A.
Okay.
In the standard diagram, the forces on these arms are equal and they are opposite. But more importantly, they act along the same axis. They are collinear.
If they're collinear and opposite, they should just cancel each other out, shouldn't they? Like a tug-of-war with no winner.
Exactly. They cancel out completely. So no net force and no torque from these two arms. Now what about the side arms, the left and right sides?
Do they also cancel out?
Well, the forces are equal and opposite, yes. One might be pushing into the page and the other pulling out of the page. But, and this is the absolute key, they are not on the same line. They are not collinear.
Oh, I see. Like when I turn a steering wheel, my left hand pulls down and my right hand pushes up.
That is a perfect analogy. That's what we call a couple in physics. Two equal and opposite forces acting at different points. They form a couple, and this couple is what creates the torque.
So we just need to calculate the force times the distance between them.
Yes. Torque is force times the perpendicular distance. The force on the wire is I times B, and the perpendicular distance that involves a sine component of the other side, A.
Okay.
So when you multiply them, you get torque equals I times A times B times sin theta.
Okay, I see A and B.
And what is A times B for a rectangle?
Oh, that's the area A.
Exactly. So we just replace A times B with A. And the final formula is tau equals IA B sin theta.
And if the coil has, say, n turns, many loops?
Simple. You just multiply by n. So the formula becomes tau equals NIA B sin theta.
NIAB sin theta.
NIA B sin theta.
NIAB sin theta. It has a nice rhythm to it.
It does. And before we solve a quick numerical, just want to check, is everything clear so far? This concept explainer is from ProfSam.com. That is PROFSAM.com. We want to make sure the basics are really strong.
Yes, the idea of the couple creating the torque is very clear now. That steering wheel example really helped.
Great. Let's try a worked example then, just to lock this in. This is from our source notes. Imagine a rectangular loop. The dimensions are 0.1 meters by 0.05 meters.
Okay, a small rectangle. I'm writing it down.
The current I is 2 amperes. The external magnetic field B is 0.5 Tesla. Now, pay very close attention to the angle. The angle between the loop plane and the field is 30 degrees.
Okay. Loop plane and field is 30 degrees.
We need to calculate the torque. So step 1, what's the area?
Area is length times breadth.
Yeah.
So 0.1 times 0.05, that would be 0.005 square meters.
Correct. Step 2, what is the dipole moment, M? Remember the formula?
Right, M equals I times A. So current is 2 amperes, area is 0.005, that makes it 0.01. The unit is ampere meter squared.
Perfect. Now for step 3, we apply the torque formula. Tau equals MB sin theta. But wait, what is the angle we use here?
The question said 30 degrees, right? The angle between the loop plane and the field.
And that is a classic trap. In the formula tau equals M cross B, the angle theta is between the normal to the area and the magnetic field.
Oh, the area vector. It's perpendicular to the surface. So if the surface makes 30 degrees with the field, the normal must make 90 minus 30.
Exactly. 90 minus 30, which is 60 degrees. You have to use 60 degrees in the calculation, not 30.
That is a very tricky point. So the calculation is actually 0.01 times 0.5 times sin of 60.
Correct. And sin 60 is about 0.866. So if you multiply those, 0.01 times 0.5 times 0.866, you get approximately 4.3 millinewton meters.
4.3 millinewton meters. Okay, I understood the calculation steps, and I almost fell for that angle trick.
Good. And this principle we just used isn't just for math problems. It's a direct foundation for the moving coil galvanometer.
The device that measures current.
Yes. In a galvanometer, a spring provides a counter torque that balances this magnetic torque, and that's how we measure current. We'll study that in the next topic.
I remember seeing the diagram in the book. It has a spring and a pointer. It makes so much more sense now.
Good. Now let's talk about the silent killers. These are the common mistakes where students lose marks in the exam.
Yes, please tell me. I don't want to lose marks on silly mistakes.
The first one is exactly what we just saw, the angle confusion.
The theta problem.
Yes. So many students think theta in the formula is the angle between the loop surface and the magnetic field.
Yeah.
But you must remember, in the vector formula tau, M cross B, theta is the angle between the area vector and the magnetic field.
And the area vector is just the normal.
Correct. So here's a classic exam hook. If the question says the field is in the plane of the loop, What is the angle you use?
If the field is in the plane, then the angle between the plane and the field is 0. But the normal is perpendicular to the plane, so the angle between the normal and the field must be 90 degrees.
Brilliant. So theta is 90
Yeah.
and sin is 1, and that gives you the maximum possible torque.
Okay, so in the plane means maximum torque. I'll write that down.
Good. Misconception number 2 is about net force versus torque. A question might ask, a current loop is placed in a uniform magnetic field. Does it move?
Does it move? Well, it rotates.
It rotates, yes. But does it translate? Does it move sideways or forward and back?
I'm not actually sure.
The answer is no. In a uniform field, the net force is 0, We saw how the opposite forces cancel out, didn't we?
Right.
So there's only torque, it spins, it does not move sideways.
So uniform field means twist only, no push.
Exactly. Twist only, no push. Remember that phrase?
Twist only, no push. Got it. But wait, what if the field is not uniform?
That's a very good question. If the field is non-uniform, then the forces on opposite sides don't cancel perfectly. And in that case, you get both rotation and detranslation, like how a magnet will jump towards a fridge.
I see.
But for your syllabus and the standard derivation, we almost always assume a uniform field.
Okay, understood.
Now, and make sure you never forget this, let's create some memory anchors.
I like the mnemonics.
Okay, for the formula, just remember the phrase.
TAU equals mu b sin theta.
TAU equals mu b sin theta.
You can think of it like a sentence. Torque amounts. Using mu b times sin theta, the mu just stands in for the magnetic moment ma. That's helpful.
Okay, and for the direction, we have a physical gesture. Let's call the hand dipole. Hold your right hand out flat.
Okay, holding it flat.
Now curl your fingers in the direction that the current is flowing in the loop.
Fingers curling, like the current.
Your thumb will stick out perpendicular to your fingers, right?
Yes.
That thumb, that is the direction of your magnetic moment, your area vector.
So my thumb is M.
Yes. Now imagine the invisible field lines in the room. Just rotate your hand until your thumb points in the same direction as those field lines. That is the stable position where torque is 0.
Okay, thumb aligned with the field. That feels stable. It feels right.
Good. And one last association for you. The merry-go-round in a windstorm.
A merry-go-round.
Imagine a merry-go-round is your loop. The wind is the magnetic field. The wind pushes the merry-go-round and creates torque. It spins it. But it doesn't pick up the entire merry-go-round and throw it across the park.
Right.
That would be a net force.
Right.
The wind just spins it.
Mm.
Torque, but no translation.
That's a great visual. The wind spins it, but doesn't move the whole structure.
Precisely. Okay, now let's just summarize everything we've learned today with a quick 3-point summary.
Okay, I'm ready. Taking notes.
Point number 1. A current-carrying loop acts as a magnetic dipole, and its moment is given by M equals NIA.
M equals NIA. Check.
Point number 2. In a uniform magnetic field, this loop experiences a torque, given by tau equals M cross B, or NIAB sin theta, but it experiences 0 net force.
Torque, yes. Force, no. Check.
And point number 3, this torque always tends to align the dipole moment with the magnetic field. That position is called stable equilibrium.
Alignment is stability.
Got it. If you understand just these 3 points, you can tackle any conceptual question on this topic. And remember, this is the key to understanding how motors and galvanometers work.
I feel so much more confident about this, both for the derivation and the numericals now.
That is what we aim for. To get maximum marks in 12th CBSE Physics, Chemistry, and Maths, visit ProfSam.com.
That is PROFSam, right? Thank you so much. This was really, really helpful.
You are most welcome. Keep studying hard. Goodbye for now.